Welcome to the Shikasa Boo Motor channel. This channel provides easy-to-understand explanations of car mechanisms. The Jeep CJ2A, introduced in 1945 as a civilian adaptation of the military Willys MB, is regarded as the world's first AWD passenger vehicle. Arguably, the most advanced AWD system today is the one found in Ferrari models, where the rear wheels are powered by an engine combined with an electric motor, and the front wheels are driven by two electric motors. That said, the Jeep and Ferrari systems were designed for entirely different purposes. In this video, we explore the structure and operation of various AWD systems, spanning from the simple Willys Jeep to advanced Ferrari models. This is the simplest AWD system configuration. Engine output is distributed to the front and rear propeller shafts through gears. This system has a significant drawback. When a vehicle goes around a curve, the four tires follow paths of different lengths. In other words, the four wheels rotate at different speeds. The difference in rotational speed becomes more pronounced as the radius of the turn becomes smaller. On slippery surfaces, differences in wheel speed can be absorbed by tire slip. However, on paved roads, the tires cannot slip, so the vehicle can no longer move forward, as if strong braking were applied. This behavior is commonly known as drivetrain bind in AWD vehicles. Due to this phenomenon, this configuration has actually not been adopted in any production passenger AWD vehicles. The simplest way to prevent this phenomenon is to use AWD on low traction surfaces, and switch to FWD or RWD on paved roads. The transfer case is equipped with a coupling on the front output side, enabling the driver to switch between AWD and RWD by operating a lever located next to the transmission shift lever. This system was used on the Jeep CJ2A, and is still used in some modern cross-country AWD vehicles today. However, modern part-time AWD vehicles activate the coupling electronically by operating a switch or dial on the dashboard rather than a lever. While AWD is obviously advantageous on unpaved roads, it also offers advantages on paved roads. It improves straight-line stability at high speeds, and enhances stability during acceleration when the road surface becomes slippery, even on paved roads such as in rainy conditions. The first mass-produced passenger vehicle to adopt full-time AWD was the first-generation Range Rover. It featured a bevel gear differential in the transfer case, which prevented drivetrain bind during tight cornering. However, with this configuration, the vehicle will not move if one wheel completely loses traction. If you're wondering why this happens, please watch the video explaining how differentials work. A link can be found in the description. To prevent this, first-generation Range Rovers up to the 1988 model year were equipped with a manual differential lock similar to that of part-time 4WD systems, while later models were fitted with a viscous coupling. Viscous couplings will be discussed later. The Audi Quattro, introduced in 1980, adopted this system for a vehicle designed more specifically for on-road driving. Early models up to 1987 used a differential lock, while later models adopted a worm gear-type torsen limited slip differential. In torsen-equipped models, the normal torque split is 50-50, but up to 80% of the engine torque can be distributed to either the front or the rear axle. However, for on-road sports models, a 50-50 torque split can compromise handling performance. If we assume the tire's total grip is 100, it can only be shared between longitudinal and lateral forces up to that limit. For example, if 40 of the available grip is used for acceleration, 60 remains for lateral grip. If 80 is used for braking, only 20 is left for lateral grip. In an AWD vehicle, longitudinal forces from engine output act on the front tires during acceleration, while those from engine braking act on them during deceleration. As a result, the front tires have less lateral traction available, which increases understeer. If you'd like to learn more about understeer, please check out this video. You'll find the link in the description. To address this issue, it is necessary to reduce the amount of engine torque sent to the front wheels. In other words, an uneven front-to-rear torque distribution is required. Here, we will explore two types of center differentials with an uneven torque distribution. The first is a planetary gear center differential. Engine output is transmitted to the planetary carrier through a set of gears. Output from the sun gear is transmitted to the front wheels, while the ring gear drives the rear wheels. When driving straight on a flat, paved road, that is, when no torque difference exists between the front and rear wheels, the planetary gear set rotates as a single unit, and the front and rear wheels rotate at the same speed. To explain uneven torque distribution, let us consider a vehicle raised on a lift, with the front wheels held stationary by applying a brake. The ring gear has 60 teeth, and the sun gear has 24 teeth. If the input rotational speed is set to 1, the ring gear speed output to the rear wheels is increased to 1.4, while the sun gear speed is 0 because the front wheels are held stationary. Because speed and torque transmitted through gears are inversely related, when the speed increases by a factor of 1.4, the torque is reduced to approximately 0.7 times. This means that a torque of approximately 0.3 of the input torque is required to lock the planetary carrier. In other words, this differential transmits 70% of the input torque to the rear wheels and 30% to the front wheels. The torque distribution ratio can be determined by the tooth counts of the planetary gear set. Many vehicles use a torsen-type center differential that integrates a limited slip mechanism into this planetary gear center differential. Its key features are the use of helical gears for the planetary pinions, and the fact that the planetary pinion shafts are not fixed to the planetary carrier. The planetary carrier transmits torque by applying force to the sides of the planetary pinions. When the front and rear wheel torques are equal, the planetary pinions do not rotate, so the differential operates in the same way as an open differential. To illustrate the torque difference between the front and rear axles, the planetary carrier is fixed, and the ring gear and the sun gear are rotated in opposite directions. When a torque difference arises between the front and rear wheels, the planetary pinions tend to rotate, but friction at the contact interface between the planetary pinion sides and the planetary carrier produces a force that opposes this rotation. In addition, because the planetary pinions are helical gears, axial forces are generated along the gear axis during rotation. This force presses the planetary pinions against the side faces of the ring gear, generating friction, which also resists the rotation of the planetary pinions. As a result, when a torque difference occurs, torque is transferred from the slipping axle to the non-slipping axle. The first vehicle to adopt this type of limited slip differential was the Audi RS4 in 2006. The second example is the crown gear center differential, adopted by Audi for the 2015 RS5. It consists of 2 crown gears and 4 pinion gears. Engine output is distributed to the rear crown gear and the front crown gear by pinion gears. Those 2 crown gears have different diameters, and the pinions mesh with them at different positions. As a result, different amounts of torque are applied to the output shafts of the 2 crown gears. Under normal driving conditions, the Audi RS5 distributes 40% of the torque to the front wheels and 60% to the rear. In addition, this differential also provides a limited slip function. Due to the shape of the crown gears, a separating force is generated that pushes the 2 crown gears apart when the pinions rotate. This force actuates the front and rear clutches, transferring torque from the slipping axle to the non-slipping axle. In the Audi RS5, torque can be distributed between the front and rear axles from 85 to 15 to 30 to 70. The system Nissan introduced in the R32 Skyline GTR in 1989 distributes torque using an electronically controlled hydraulic multiplate clutch without a center differential. Depending on driving conditions, the system calculates the optimal torque distribution and can control it over a range from 0 to 100 to 50 to 50. For instance, on corner entry, torque to the front wheels is reduced to 0 for sharp turn-in, while on corner exit, a 50-50 split is used to put maximum engine power to the ground. Subaru employs a similar system as well. The system normally operates with a 60-40 torque distribution, which can shift from 50-50 to 100-0 depending on driving and road conditions. The Toyota GR Yaris also features an active torque distribution AWD system with a multi-plate clutch coupling, and its design is extremely distinctive. The total rear reduction ratio is approximately 5% lower than the front reduction ratio. During straight-line driving, all four wheels rotate at the same speed. Therefore, the front propeller shaft rotates faster than the rear propeller shaft. Please note that the actual GR Yaris has a transverse-mounted engine and does not use a front propeller shaft. For ease of understanding, the configuration illustrated here is used. Because the front and rear propeller shafts rotate at different speeds, the clutch is continuously slipping. In this state, the drive torque distribution is controlled between 60-40 and 30-70 by varying the clutch clamping force. Since the clutch is continuously slipping, the AWD coupling inevitably generates heat. However, Toyota's engineers state that this remains within acceptable limits. If Toyota says so, it's probably fine, apparently. The AWD system that Audi uses in the RS3 is also distinctive. Instead of using an AWD coupling, it is equipped with two sets of clutches inside the rear differential. By controlling the two clutches simultaneously, the system can vary the torque distribution between the front and rear axles. During cornering, the system enhances cornering performance by increasing the clamping force of the outer wheel clutch while reducing that of the inner one. This function is commonly referred to as torque vectoring. The clutches used in these systems were originally actuated by electronically controlled hydraulic pressure. However, in recent years, the use of electric motors or electromagnets has made faster response possible. Passive torque distribution is a system in which the vehicle normally operates as a FWD vehicle, and torque is distributed to the rear axle only when wheel slip occurs at the driven wheels. In this section, we will look at electronically controlled systems and viscous coupling systems. The system configuration of the electronically controlled type is not significantly different from that of an active control system. Under normal driving conditions, the clutch is disengaged and the vehicle operates in FWD. When the system detects slip at the drive wheels, clutch clamping force is increased to distribute torque to the rear axle. Today, this system is widely used in AWD vehicles such as SUVs and sedans that are not sport models. In some of these models, the system controls front-rear torque distribution not only when wheel slip occurs, but also during cornering, acceleration, and deceleration, thereby improving vehicle stability. Therefore, the distinction between active and passive control is becoming increasingly blurred. However, even if the system configuration is similar, there are significant differences in the fundamental control philosophy and the capacity of the rear driveline depending on the vehicle's character. Systems that use a viscous coupling rely on purely passive control. A viscous coupling has a structure in which multiple plates are installed between the coupling hub and the outer case, similar to a multi-plate clutch. The coupling is filled with a very high viscosity silicone oil. Consider a situation in which the front wheels slip during vehicle launch. When the front wheels slip, the plate on the front axle side rotates, while the plate on the rear axle side remains stationary. At the interface between the rotating plates and the silicone oil is dragged along by the plates. Shear resistance is generated within the silicone oil, and as a reaction, a braking force acts on the rotating plates, while a driving torque acts on the stationary plates. Through this mechanism, the viscous coupling distributes torque from the slipping axle to the non-slipping axle. Although it offers a cost advantage, its performance is limited because the differential limiting force is applied only after a rotational speed difference has occurred. For this reason, Since the 2000s, it has been adopted only in some relatively low-priced small cars. In hybrid vehicles, AWD systems that integrate an electric motor into the driven axle are employed. In FWD-based AWD vehicles, a single motor is integrated into the rear axle. Basically, the vehicle operates as FWD under normal driving conditions, and switches to AWD when front-wheel slip occurs. However, it also distributes torque to rear axle during cornering, acceleration, and deceleration, to enhance driving stability. Some hybrid models, such as the Ford Escape and the Honda CR-V, adopt a mechanical AWD system equipped with a propeller shaft. Some high-performance hybrid models use a three-motor system, with the engine and one motor driving the rear axle, and separate motors driving each front wheel. This system was first introduced on the second-generation Honda NSX in 2016, and continues to be used today in models from Ferrari, Lamborghini, Aston Martin, and others. During cornering, torque to the left and right front wheels is controlled independently to produce a torque vectoring effect, thereby improving cornering performance. Now, let's return to full-time 4WD systems with an open center differential. As mentioned earlier, in this system, if one tire completely loses traction, all of the engine torque is transmitted to that tire, preventing the vehicle from moving off. Many AWD vehicles prevent this by selectively applying the brake to the slipping wheel. This suppresses wheel spin, allowing engine torque to be directed to the wheel that still has traction, enabling the vehicle to move off. This function is known as a brake-limited slip differential. Thank you for watching. If you enjoyed this video, please consider subscribing to the channel. We'll see you in the next video.